We're going to be doing the chapter review questions now. It says a rock is dropped from a bridge into a valley. Earth pulls on the rock and it accelerates down. According to Newton's third law, the rock must also be pulling on the earth. Newton's third law says for every action force, there's an equal and opposite reaction force. So if this is attracted to the earth, which we call gravity, the earth is actually attracted to the rock with the exact same force. The earth does not seem to accelerate. Why? Because your acceleration is proportionate or inversely proportionate to your mass. So if you've got a really big mass, that means you have a really low acceleration as long as the force stays the same. Number 60, the second question, it says Joyce and Afua are skating. Joyce pushes Afua, whose mass is this, with a force of that. What is her resulting acceleration? So I'm looking for the acceleration. She's got a mass of this and a force of this. Now, some people just blindly go plugging numbers in, and it's going to actually work for you this case. But you got to be really careful. It is always helpful to draw a picture. You've got this young lady, and she's got the force of gravity, and it's 40 times 9.8. So it comes out to 300. She actually weighs 392 newtons. And there's an upward force provided by the floor in the normal force, which is also 392. And she's being pushed this way with a force of 5 newtons. So some people don't know, do I multiply this by 9.8? Do I divide that by 9.8? What do I do with everything? You're going to plug it into the F equals ma. And this is the net force behind you. So these two are canceling because they're equal and opposite. So our net force is actually 5 newtons. My mass is 40. So I can find my acceleration. My acceleration comes out to be 0.13 meters per second squared. Next one. Number 61. A car of mass this slows down. So I've got a car. It weighs a certain amount. 2,300 times 9.8 comes out to 22,540. There's an upward supporting force, the normal force. And then it's slowing down, so there's some braking force. I'll just call it F braking. I don't know. And it says, what is the magnitude? The magnitude means how big. Like, how big is the force? It doesn't matter that it's backwards, so you don't have to use negative numbers here. So I'm going to plug it into my equation, the net force, F equals ma. My net force is the braking force because these cancel, so my net force is that. My mass is 2,300, and my acceleration is 3. Now again, you could put negative in there, and it doesn't matter because it's only looking for the magnitude. The braking force comes out to be 6,900 newtons, like that. Number 64. Your motorcycle weighs this many newtons. What is its mass? Remember, in order to go from weight to mass, it's still an application of F equals ma. You always use 9.80 when you're going from weight to mass. This is 2450, so we solve for the mass. 2450 divided by 9.8 comes out to 250 kilograms. Number 68, drag racing. It says a dragster is starting from rest and it gets a speed of this in this many seconds. Find the average acceleration. So for part A, I'm looking for the acceleration. I know that it starts from rest. It attains a speed of 26.3 meters per second, and in this many seconds. So I'm going to plug it into the equation that doesn't use the letter D in it, and that's just VF equals VI plus AT. So my VF is 26.3, my initial velocity is 0. I'm looking for the acceleration, and the time is 0.59. So I take 26.3, and I divide by 0.59, and it comes up with 45 meters per second squared. That's part A. Part B, it says, what is the magnitude? Again, magnitude just means how big. How big is the net force on the dragster? I know the mass of the dragster is 873, and the acceleration is 45. So when I take 873 and I multiply by 45, it comes out to be 39,000 newtons. Part C, assume that the driver has a mass of 68 kilograms. What is the net force on that one? F equals ma. We know the driver has a mass of 68, and we know that we're looking for the force. So what's the acceleration? Turns out the person's actually in the car, so they have the same acceleration as the car, 45. So when you take 68 times 45, you end up with 3,100 newtons. And doing a quick Google search, this is right around like 660 pounds, which is quite a lot of force, but not unheard of because you're going probably 4 G's right there. So you weigh 4 times what you normally weigh. The next question, number 70, it says a grocery sack can withstand a maximum of 230 newtons. I'll draw myself a little grocery sack here. We know that it's 15 kilograms. So you multiply that by 9.8 and you figure out that it's how much it weighs. Its force of gravity is 147 newtons. And we're pulling up on it. And it says it's lifted with an acceleration of this. So you know that it's accelerating this direction with an acceleration of 7. So what is that pull force? And really the big question is it bigger than that? So what we're going to have to do, we know that it's bigger than 147. So we're going to put it into this equation. F equals ma. Now the net force, we've got two forces battling it out. I'm going to make up positive. I've got a pull force, and I've got gravity pulling down. The mass is still m, and the acceleration is still a. So my pull force, I don't know. I know my force of gravity is 147. I know my mass is 15, and I know the acceleration is 7. So I take 15 times 7, and I add 147 to it, and it comes out to be 250. That's bad. Because 250 is definitely bigger than its maximum force of 230, which means it's probably going to break. Number 73, a diver is jumping off of a tower. So you've got a tower above some water. And this diver jumps off. And they accelerate into the water, and then they hit the water, and they slow to a stop. So there's actually two phases to this that I like to say. I call phase 1 and phase 2. Phase 1, they're accelerating down. Phase 2, they're accelerating this way. So in each case, my initial velocity here is 0. The question wants to know, find the diver's velocity. That's what we're looking for. I know the acceleration is 9.80 because that's what it is in free fall, and the distance is 10 meters. I get that from the tower. So I'm going to plug this into the equation that doesn't have the letter t, which is Vf squared equals Vi squared plus 2AD. My final velocity, my initial velocity. So I solve it for Vf, and it comes out to be equal to 14 meters per second. That's part A. Part B, it says the diver comes to a stop. So here's the thing. the diver, whatever his final velocity is here, that's his initial velocity when it enters the water. So the diver's initial velocity when they enter the water is actually 14. Their final velocity is 0. They come to a stop, and then they do so in a distance of 2 meters. We are looking for find the net force. So F equals ma. We're looking for the net force. So we have to know the diver's mass, which we do, 65. And we have to know the diver's acceleration. We're going to get it from right here. We're going to use all this stuff to tell me what the acceleration is. So we're going to use this equation, the one that doesn't use time in it again. So VF squared equals VI squared plus 2AD. Final velocity is 0. Initial velocity is 14 squared. 2a, and my distance is 2 in this case. So solving that, 14 squared, 196, move it over, divide by 4, and it comes out to be 49 meters per second squared. So that's what I put in here, 49. So to figure out how much force is acting on this person, you take 65 times 49, comes out to 3,200 newtons. That's how much force is acting on this person. Because when the person's in the water, that force is slowing them down. It's drag, just kind of like going through the air, except it's now you're going through water. The last question, it's got a student in a bathroom scale on an elevator. So when they're at rest, so here's the person in their elevator. Here's their bathroom scale. They weigh a certain amount. She has 836 newtons of weight. Now, if the elevator is still, when the elevator is still, she's got an upward force, and this is what the scale reads. The scale is going to read what the normal force is. And it says that the normal force actually is a lot bigger. The normal force in one case comes out to be 936, which means that she's accelerating in this direction. And it actually wants to know, find the acceleration. So we're going to use F equals ma. So the net force, there are two combating forces here. I'm going to make up positive. I've got a 936 Newton force up, and I've got an 836 force down. Her mass is this number divided by 9.8. So you take that number and divide by that, and you get 85.3. And then you can find her acceleration. And that acceleration comes out to be 1.17 meters per second squared. That's part A. Part B, you've got the same setup. Except now it drops to 782. So now the scale reads not a bigger number, but it reads a smaller number. So, which means that she is accelerating in this direction. So figure out what that acceleration is. The net force, mass times acceleration. The net force, two combating forces again, 782 and 836. Her mass is 85, same mass as what it was, 85.3. And her acceleration. Solve that for the letter A, and it comes out to be 0.633 meters per second squared. So that's part B. Part C, it says, using your results, explain which change in velocity, starting or stopping, takes longer. Okay, so in part A, the elevator moves up. So I think this is where you're starting. You're starting your movement. And then as the elevator approaches, so I'm going to assume that this is stopping.